Run one update in Postgres. Watch what actually happens, because it's not what you think. The database doesn't change your row. It writes a brand new copy and leaves the old one lying right there, dead. Your table is a graveyard. Every table you own is quietly full of ghosts. And that one strange choice is the whole reason Postgres can run thousands of transactions at once, without them tripping over each other. It's called MVCC. By the end of this, you'll know how it keeps reads and writes from fighting, why it fills your disk with corpses, and how a 2 billion transaction clock can take the whole database down. I'm at pattern repetition. Let's get into it. MVCC, multi-version concurrency control. 4 intimidating words for one simple deal. Keep every version of a row around just long enough that nobody has to wait their turn. Before we get to the ghosts, one obvious question: why not just lock the row, change it, and move on? Watch that idea fall apart. Start with the naive version. One writer grabs the row and everyone else waits in line. Simple, correct. And it collapses the second you get real traffic. Readers stack up behind writers, writers stack up behind readers. Your database spends its whole day standing in a queue instead of doing any work. Postgres makes a different bet, and the manual sums it up in one line. Reading never blocks writing, and writing never blocks reading. Hold on to that sentence. Everything else in this video is just the machinery that makes it true. There's a catch though. It's the entire back half of this video. All those old versions don't clean themselves up. Keep every version of every row, and sooner or later your disk fills with the dead ones. To pull this off, every single row in Postgres carries 2 numbers you've never seen. Time to meet xmin and xmax. Every stored row, Postgres calls it a tuple, rides around with a little header. Xmin is the transaction that created this version, xmax is the transaction that deleted it, or 0 if the row is still alive. Then a physical address, then finally your actual data. That's 23 bytes of bookkeeping stapled to every row you own. Now the idea that ties it all together, a snapshot. The instant your transaction runs a query, Postgres freezes a point in time. Straight from the manual, each statement sees the data as it was some time ago, no matter what's changed since. Your query lives in that frozen moment. So which copy of the row do you actually see? The rule is almost boring. A version is visible if the transaction that created it committed before your snapshot, and the transaction that deleted it hasn't. Created in your past, not yet deleted in your past. Run that tiny check on every row, and you've got the whole visibility engine. Theory's done. Let's watch what actually lands on disk the moment you change one number. You subtract $100 from account 42, feels like a single edit. Under the hood, Postgres never touches the old row. It stamps the old version's xmax with your transaction ID, then writes a fresh version with xmin set to that same ID. Peek at those hidden columns, and there it is. A brand new row version born from transaction 5001. So one logical write leaves 2 physical rows behind. The new one is live, the old one is dead but still parked right there on the page, because some transaction that started before you might still need to read it. Postgres isn't naive about this. If your update stays on the same page and doesn't touch an indexed column, it takes a shortcut called a hot update, added way back in 8.3. The dead version gets cleaned up in place, and the indexes never even have to know. A huge chunk of your write traffic gets quietly cheaper, for free. And here's the payoff for all that trouble. Transaction A starts reading. Transaction B updates the very same row and commits. A keeps right on reading, and it still sees the old value, because that old version is still the truth for a snapshot. 2 transactions, 1 row, 2 different answers. Nobody waited. So how strict should that snapshot actually be? Postgres hands you a dial for exactly this, and honestly, most people never touch it. The SQL standard lists 4 isolation levels. Postgres lets you ask for all 4, but it really only implements 3 because its weakest mode already behaves like the next one up. Climb the dial and it rules out more of these classic concurrency bugs, the dirty reads, the phantoms. At the very top, none of them are allowed at all. The default is read committed. Every statement gets a fresh snapshot, so two selects in the same transaction can genuinely hand you different rows if someone commits in between them. Turn the dial up to repeatable read, and that snapshot freezes for the whole transaction. You get consistency. But now a conflicting write throws an error, and retrying it becomes your problem. And that error is the contract working exactly as designed. Repeatable read is telling you someone changed this row out from under your snapshot, so it flatly refuses to guess what you meant. Catch it and run the whole transaction again from the top. At the top of the dial sits Gageful at the end. Postgres has a genuinely clever take on it. It watches for dangerous read-write patterns between transactions using predicate locks that never actually block anyone, spot a set of transactions that couldn't have happened one at a time, and it aborts one of them. It really does make concurrent transactions behave as if they ran single file. So MVCC buys you all of that concurrency. Now the bill arrives, its name is dead rows. Every update and every delete leaves a dead version behind, and they pile up fast. Postgres will happily show you how bad it's gotten. One busy table here, 1 million live rows and 250,000 dead ones just sitting there eating pages and dragging down every scan that walks past them. The cleanup crew is called vacuum. It walks the dead rows and marks their space reusable. You don't run it by hand. Auto vacuum runs in the background, and by default it only wakes up for a table once roughly 20% of it has gone dead. On your hottest tables, you want that number a lot lower. Here's a gotcha that catches almost everyone. Plain vacuum makes space reusable inside the table, but it does not hand it back to your operating system. For that you need vacuum full, which rewrites the entire table and grabs a lock that blocks every other query. On a big table, that's a scheduled outage. Plan it. And this is the one that quietly takes down real systems. Vacuum can only remove a dead row once no snapshot still needs it. Leave one transaction open, a forgotten session, a stuck report, and it pins that line in the past. Postgres can't clean up anything newer, so dead rows stack up across the whole database while one idle transaction sits there doing nothing at all. There's one last consequence of stamping every row with a transaction ID, and it's the single scariest number in Postgres. Those transaction IDs are only 32 bits wide, 4 billion values total. And because Postgres compares them in a circle, only about 2 billion of them can sit in your parse at any one moment. Burn through 2 billion transactions, and that counter is about to wrap all the way around. If it genuinely wraps, it's a catastrophe. Transactions from the distant past suddenly look like they live in the future, and every row they ever created turns invisible in an instant. The manual calls it, and I'm quoting here, catastrophic data loss. The data's still on disk. You just can't reach it anymore. The defense is called freezing. Once a row is old enough, vacuum marks it permanently visible and pulls it out of the counter for good. Auto vacuum starts freezing aggressively at 200 million transactions of age. Ignore it long enough and Postgres starts warning you. Then, with 3 million transactions left on the clock, it does the only safe thing it can. It stops accepting writes. And the scary part is you can actually watch this clock tick. There's one number, transaction ID age, that tells you how close each table is to the edge. Green, you're fine. Amber, auto vacuum had better be freezing hard. Red, and you're dangerously close to your database going read-only, put it on a dashboard and watch it. This is the message you never ever want to see in production. Your database gone read-only, refusing every write until you vacuum it back down to safety. Companies have taken real public outages from exactly this. Usually because someone turned auto vacuum down to save some I/O and then completely forgot about it. None of this machinery is new. Postgres has been sharpening it for more than 25 years. Here's the short version of how it got here. MVCC has been in Postgres since 1999. Hot updates made writes cheaper back in 2008. In 2011, it became the first production database in the world to ship true serializable snapshot isolation. And the one big unfinished piece, moving those transaction IDs to 64 bits so the clock can never wrap, is still being argued over to this day. So, 5 things to actually take away. Watch your dead tuple counts, not just your table size. Tune auto vacuum to fire sooner on your busiest tables. Never leave a transaction hanging open, that's the horizon killer. Wrap your writes in retry logic the moment you go above read committed, and put an alert on transaction IDH long before it's ever an emergency. That's MVCC. Postgres keeps every version of every row, so your reads and your writes never have to fight, and it quietly counts on you to bury the dead. Every table you own is full of ghosts. The good databases just know which ones to ignore. I'm at pattern repetition. See you in the next one.